Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you very much. So, thank you very much to Peter and to Andrew, particularly for inviting me to give a talk here. I was planning to spend a few days figuring out what on earth scalable language specification was before I came here. Unfortunately, the EU had other plans, so I've been learning on the fly. So hopefully what I'm going to tell you is going to be relevant to you, and I'll give my statement of what I think scalable language specification is and why this talk is relevant at the very end, and hope you agree with me. I'm very pleased to see so many talks mentioning Haskell. Egon didn't mention that I was on the Haskell design committee, and monadic I/O, amongst other things, is partially my fault. So if you hate monads, then I'm afraid that I'm partly to blame. But it was the best solution at the time, guys, and if you've got any better ideas, please do let us know. We're very open to other suggestions. I'm going to tell you about some work that we've been doing with a group of people from various universities. This is just a small part of the team. So people from Porto, the University of Porto in Portugal, from Ludwig Maximilian's University in Germany, Heriot Watt in the UK, various other institutions, all told about 20 or 30 people, far too many to list here. But these are the people who have been primarily involved in the topic of the talk, which I'm going to tell you about compositional resource analysis in Hume. If you have any questions during the talk, please don't hesitate to ask them. It helps me know that you're still awake, which is always good for a speaker. And if you don't ask me questions, then I'm liable to ask you questions. And on the whole, your questions are probably easier than mine, at least for you to answer. Okay, so don't be shy, and do show me that you're awake, especially after yesterday's very fine dinner. So, what is Hume all about? Well, as I'm sure you're aware, the embedded systems domain is incredibly important. Today, 98% of all processors in existence are used in embedded systems. Every year, the number of processors which are using is doubling. And sadly, the world that we think we live in of 32-bit or 64-bit microprocessors hasn't yet reached the masses. So 98% of the processor designs that we use today are still 8-bit or 16-bit designs. This has huge implications in terms of issues like bounding memory usage, enforcing real-time deadlines, and estimating power consumption. So in some sense, computer science lives in a fool's paradise, looking at 2% of machines that are not the ones that are really being used in the real world. And that's the domain that I'm looking at. So I'm looking at the 98% rather than the 2%, but also the implications to the 2%. We think that bounding resources is incredibly important. Here's a comment that I picked up from Greg Morissette over coffee at some conference, so it's clearly attributable. And what Greg says is that in the future, we will regard software without formal resource bounds in the same way as we regard untyped programs today.
In other words, widely used and universally applicable and generally more fun to work with.
Yes, and buggy.
Okay, thanks.
There's always one. This is, of course, a bit tongue-in-cheek. But the point is that resource bounds, they're an important tool for removing and correcting errors. And I hope we're all striving for software that works. So what I'm going to tell you about is a new direction. This is a road sign from Australia somewhere, a language called Hume. The language is named after David Hume, who was a Scottish Enlightenment philosopher and particularly skeptic. We think that if I presented the results I'm going to show you today to David Hume, he would have said to me, I really don't believe that what you've told me is actually possible. And that's the right attitude, one of deep and unfounded skepticism. What are we trying to do? Well, a number of different things. First of all, what I'm trying to do is to construct a virtual testbed for pushing back the frontiers of space, time, and power cost modeling. So what I'm trying to do is to build myself a pure virtual laboratory in which I can say, okay, I want to get rid of all these awkward and possibly important to real world issues in order to focus on how far can I actually push back the boundaries of cost modeling. Having done that, you can take the techniques and adapt them and hopefully apply them in settings that some people might use, like C, Python, other fine languages, with or without types. The second thing that we're targeting is real-time bounded space programming using a high-level notation. I'll tell you a bit more about this later on, but essentially the idea is to combine the virtues of functional programming with the virtues of finite or otherwise automata. So to use the strong connectors properties of functional programming embedded within automata to allow us to deal with real-world interactions. So this is the idea, a two-level language. And that's going to come back later. Egon said that I've done a lot of work in parallel programming. Well, of course, Hume has to be concurrent and multi-threaded, not just because of my background in fact, but also because concurrency is incredibly important if you're dealing with real-time systems, with embedded systems. Real-time systems exist in a framework where there is interaction with the real world, where you have to deal with this, in particular timeframes. If you don't have concurrency naturally built into your language, you cannot deal with this. I'll show you this later on. Unlike a lot of designs, however, what we have is a mechanism which allows for asynchronous threading, asynchronous message passing, and which allows a great deal of flexibility in terms of the triggering of computations. So essentially some sort of very fine-grained triggering technique, not fully synchronous, as you see most language designs. So asynchronicity at the language level is an important property to allow certain types of program to be written. And the final point, which is relevant to you, is that what we've got here is a language-first design. And moreover, as I'll tell you throughout the talk, it's a language where we've thought about the semantics. So in designing the language, we have thought, what does the language mean? What are the static semantics? What are the dynamic semantics? How is it possible to implement such and such a feature? Having implemented such and such a feature, how is it possible to produce a cost analysis for that feature? So unlike most language designs where people think, okay, here's a nice set of problems that I would like to deal with, one of the overriding principles in the Hume design is that whatever we put into the language has to have a known and, at least in theory, analyzable cost. Go ahead, Peter.
Have you been writing down the formal semantics as you've been designing the language?
Yes.
Good, thank you.
We have. I'm going to show you some of that as I go through the talk. Unfortunately, in the nature of all formal semantics, there are a series of documents. There are about 10 documents in total. Each of these documents contains about 30 pages of mathematical text. There's a lot of it, okay? But it has all been written down. I'll show you some of that as we go through. That's one of the things I want to show you in this talk. And one of the luxuries I'm permitting myself, because normally when I give a talk on Hume, I don't get the chance to go through all the semantics and to show all the definitions, but I'll at least give you some appreciation. Shiram.
I'm just curious what language first means, as opposed to what first is maybe...
Problem first. So what I really mean here is that it's semantics first. So we're thinking strongly about semantics. With a lot of language designs, people come along and they have a particular problem to solve. JavaScript. I've got to have a language which will deal with web browsing. Okay, quickly hack it together. If you go and talk to people in mathematics, I need to write some mathematics, right? I'll write a programming language. What do other programming languages have in it? Well, we'll just grab stuff and put it in. Oh my God, it's a horrible mess. Okay? Here, the language design is intended to be coherent and consistent. And if you're coming from the functional community, of course, we tend to do this. But other programming language designs don't always do that.
Well, the Haskell designers didn't.
We sort of did that.
The History of Programming Languages article indicates that there are two reasons for not wanting to write down the formal semantics of Haskell.
This thing is a bit of a digression, Peter, which we can have in the coffee break. But in 1990, I started working with Jon Fairbairn on writing down the formal semantics of Haskell. Okay, so the very first definition came out in 1988. I started working on Haskell in 1989. Jon at the time was looking at formal semantics. I spent some time working with Jon on a formal semantics. Essentially, the reason we gave up wasn't because we didn't think it was a good thing. It was more or less because we ran out of time, and there were more urgent things to do, like actually getting a compiler that worked. And the rest is history, as you know. So what we're trying to do in Hume? Well, we're trying to achieve a number of interesting but mutually contradictory objectives. So we want reliability and predictability. So we want software which ideally is correct by construction with a high degree of determinacy in terms of things like the scheduling, the communication, functionality, and the behavior. So unlike a lot of language designs, behavior is very important in this domain. We cannot ignore the issues to do with things like interrupts, timing, memory usage, etc. These are things that most language designs just sweep under the carpet. In Hume, we don't do that. All these things are there, they've been thought out, they've been thought about, they're apparent in the language design, and controllable to some extent. We want expressibility and controllability. So we want, ideally, to have a very high level of expressibility. Well, we're functional programmers. So we want to give you things like automatic memory management. We want to give you recursion. We want to give you the power of higher order functions. These are things which essentially have never been seen in the embedded systems domain, for reasons that people working in the domain think are very good ones. Essentially, a lack of knowledge about the space and time properties of these constructs. So this is one of the key things that we're trying to achieve. But at the same time, we do want to deal, in fact, we have to deal with low-level issues. We have to deal with issues of interrupt scheduling, FIFOs, ports, memory mapped I/O, all these dirty low-level things. They have to be there, because if you don't have these things, we can't actually interact with the real world. And this is the dilemma. We need a high level, we want a high level, but we have to deal with this low level at the same time. And finally, we want costability. We want to be able to achieve accurate cost predictions for space, time, power, concurrency, blah, blah, blah. This is what we're trying to achieve. We don't have any category theorists in the audience? Good. So I don't have to say this is not co-stability. Costability.
By cost of concurrency, you mean how many agents you have around, how many
It's not.
For example, yes, how much parallelism does the system expose? So how many concurrent agents could be working at a particular time? And in some systems, this is an interesting metric. So it's just another metric that we might be interested in.
Each of them will have space and time and power.
Yes.
Okay.
But it's something you might want to tune. So for example, this doesn't happen at the moment, typically, but we might want to have a multi-core implementation of an embedded system. So we might want to know that our system has adequate parallelism to keep this multi-core system occupied. Okay? If we design a system without taking that into account, it won't scale. And in the future, maybe in some future hardware, then it will become unusable. We'll have to throw the design away and start from scratch. So this could be an important parameter. I'm only throwing that in there. I'm throwing that in there essentially not because we've looked at it yet, but because it's something which is a bit unusual and people don't normally think about. Okay, but it is another metric that you might want to deal with. And as I said, everything with a strong semantic foundation. So this is what Hume looks like. Essentially, boxes structure processes. So we have a system which comprises a static network of linked boxes. The boxes are linked using an asynchronous communication mechanism. So this means that the box 2 doesn't necessarily have to wait for all of the results of box 1 before proceeding. Maybe it only needs the first one or the second one. Maybe it's a merging box, something of this kind. It could even be an emitter box that doesn't need any inputs at all. That's fine. Or a sink that doesn't produce any outputs. Also fine as part of the design. So all these designs are permitted. Box 2 produces some result based on some of the box 1 inputs, passes on to box 3 with some other input from box 1, and then produces some output. So this is how the system communicates with the real world. So we take input from the real world, we produce output to the real world. And in a real embedded system, there might be multiple input sources, there might be multiple output sources. The inputs and the outputs can come anywhere in this diagram. They don't have to come at the end, they don't have to come at the beginning. We could have box 2 taking some input from some external input, producing some external output, for example. All under strong timing control.
Where's time in this whole picture?
It's implicit. So time is in the time taken to process the box, so to execute the code in the box. Time is associated with the time between receiving an input and processing it, and the time between taking the original input of the system and producing it at the end. And that's what we want to produce. What we need to produce are reactivity times for each of the individual boxes and overall system reactivity times. So when you hand in an input, you get an output within a certain amount of time.
And how
That's
is
where the time
synchrony going to work into that?
Well, we have to take it into account. It has to be baked into the model. So we have to consider what are the possible interactions. I'm talking about asynchrony at the language level rather than asynchrony exactly at the communication level. So what I mean by asynchrony is this box, for example, may only require one of these 2 inputs. And then we have to reason about that. Okay? But not that we have asynchronous hardware with no timing properties.
No, but
There is a timing property.
You have typically a network
Yes.
with uncertainty about when things are going to arrive.
We control as much as we can of the network. The communication is internal. This is not going across. It's not going across a processor network. What I'm talking about here is a program design. If I have a physical network involved, then that has to be a network that has real-time properties. So absolutely everything has to have known cost. The language has to have known cost. The constructs have known cost. The hardware has known cost. This is essential in this framework. Okay, so most of these costs in typical implementations will simply be memory cost. So these link costs are basically memory costs, which are almost instantaneous, but still take some time. And then we have to worry about what the processor can do in terms of scheduling, etc. So we have to layer that up. But that's all dealt with.
So does it mean there are 2 meanings of these errors? Because we see there are these errors coming from or going to outside and the inside ones, and they are distinguished only by the endpoints.
Yes. No, they're all the same. They're all the same thing. This is a uniform model.
It's communication.
It's communication.
Okay.
How it's implemented potentially is different. Okay. So here, for example, this could be communication to a FIFO buffer. In Hume, we treat a FIFO buffer as a pseudo box. So it looks like a box, it has inputs, it has outputs, it does stuff, it's triggered, it does stuff. Okay, so it's all part of the same model. And these connections, these are all wires.
So if something goes from box 1 to box 2, for example, that would be a time step?
Yes, absolutely. There is time everywhere in here. Okay. I thought you were going to ask me about this arrow here. This is a feedback arrow, but it's a feedback from one iteration of a box to the next. So the idea that boxes work in lockstep, they do something, they take some inputs. Based on the inputs at some snapshot time, they will do some computation. This is the functional programming part. And having produced the results, they then feed them out. Now, the way that the system is entirely stateless. The way we model state is by taking an explicit output and passing it back in. And this has some advantages in terms, A, of making the time very explicit, but also in terms of making the space usage very controllable, very explicit. I'll show you later, perhaps, that we effectively get a kind of, for free, copy and compact garbage collector just from doing this. Okay. And moreover, one which has real-time properties. So everything is controlled, all the time is known, all the space is known. Quite nice properties. So from Tony's talk, essentially the model that I've got is one of concurrency. All the boxes are, in principle, acting together, and exactly when they stop, when they synchronize, is partly down to the system. Okay, I'm going to move on a bit because I want to get to the semantics, which people want to see. This is what a box is. You've probably got an intuitive idea. So basically, this is for a simple AND gate. This is something which is synchronous, of course. So for example, we take A and B, which are Boolean. We produce a result, which is the Boolean. The way that we do this is by matching. So it's a functional-like matching syntax. And for example, what we're doing here is say, if you've got two false inputs, you produce a false input. If you've got two true inputs, you produce a true input. So this is a very, very simple example of a box. Okay, and typically, they're much more complicated. And typically, there will be computation here. So this is a much more complex model than I'm just showing.
But such a computation you consider as, so to speak, zero-time atomic?
No. No, absolutely I don't. I consider all of the time that it's taken to produce the result. I'm interested in the time from the consumption of the inputs to the production of the outputs.
It is, so to speak, one step of that box.
One step of the box, yes, but not zero time. Absolutely not zero time.
I see. But it's one step of the box.
One step of the box. So boxes in Hume repeat indefinitely. So the idea is that a box just sits there, it consumes input, it produces outputs, until there's no more input. So the termination condition is there is nothing else to do. Okay? People often talk about termination analysis. If you have a real-time system, if you have a system controlling an aircraft engine, you do not want termination of the system. This is a bad property. In fact, I want the opposite. I want liveness. I do, however, want to be able to demonstrate that the code within the box terminates within some known time. This is the essential fundamental building block that I'm going to use in my language design. Sharon.
In fact, I got the impression that you count the time for the boxes, but the propagations were zero time. Is that correct?
No, the propagations have time too.
They have times as well.
They have times as well.
And when you said one, you just said the phrase something like one unit or one
Iteration.
one iteration, but that doesn't mean you assign it. It's not an abstract time. All boxes are not one, right? I mean,
No.
you compute out
based
on the costs of things and do a WCET or something.
Some
like
boxes may
Yeah.
be thousands, some may be one.
Exactly.
One is impossible, pretty well impossible, in fact, because everything takes some time, which is more than one. The exact unit we'll see later, but typically what I think of is in terms of clock cycles for time, and typically what I think of for memory are small units, bytes or words of memory that's been allocated or used. Okay, so this is what I'm thinking of with my units.
Still puzzled by a detail. You said that so the termination is not your issue, but that thing will end if there is no input. So
Yes.
if it is possible that there is no input, then the in should go not into bool, but bool plus unlef.
If there's no input, then the box will simply suspend. There's no undef.
But what's the value of in if there is no input?
There is no input.
So possible value of a and b can be unlef.
No, it can never be undef.
It's a reactive system, right?
It's a reactive
it just never
system.
fires. So
That's right. Either it produces, in this situation, either it has inputs and produces an output, or it doesn't. It does nothing. It's not undefined. It's nothing. Semantically nothing.
Okay, I see.
Yeah.
Yeah, okay.
And that would take zero time. That would take zero time. Okay, here's a more complex example just to illustrate some of the more powerful features of Hume. So here what I've got is a simple vending machine. Essentially what we have a cash holder. We put coins here, nickels or dimes, into the machine. We have a keypad to say, I want a tea or a coffee or whatever. A hot drink is my favorite type of drink. There's a vending unit that actually gives me a tea or a coffee. And the interesting bit is this red box, the control box, which is the logic of the system, central logic of the system. So what it's doing is taking button presses, it's recording the coins that have been input, it has some internal value of the coins that it has so far, and then what it can do is either instruct the vending unit to dispense the drink, or it can instruct the cash holder to return coins if you said you want to cancel your transaction and get back the money you've put in. So a very simple reactive system. Here's the complete definition of that system in Hume. I show this to hardware designers and they're usually quite impressed by this. So we have a Haskell-like specification of some enumeration types, so the coins, nickels or dimes, the drinks, teas or coffees, the buttons I can press, coffees, teas, cancel, give me the money back. Here is the definition of the box. So what I'm doing is taking in the coin, taking in a button, taking in the initial value. The result of the box is either to dispense a drink, to produce an updated value internally, or to instruct the return unit to give back a certain amount of money to the user, which will be the value that you have. Here's the complete definition. If I get a nickel, what I do is to increment the value by 5. If I get a dime, by 10. Hopefully I've got this right, Sharon. Good. It's easier in the UK, we have 5p and 10p. Or I have a coffee or a tea or a cancel. If I have a coffee or a tea, what I do is I call the vend function. This is essentially an arbitrary use of the function to show that we can call functions within the box. What I do is vend a coffee costing 10 with the current value. Or a tea might cost 5. And if I press the cancel box, well, the new value of the coin internally is 0, and I return the current value B. And you can prove properties of this, of course, very easy to take this, and to prove that you always give out the money that you put in, that you never dispense more than the amount of money you've put in, you never dispense if there's no money, and so on. You can do this fairly easily.
Now you said status, but what if there is no coffee anymore, but I put the coin? So isn't it something like state which you have to take into account?
No, there should be another input.
But this is a strange input. I mean, it's a machine which has or does not have.
No. This is a reactive real-time system. In such a system, everything which you need to consider should be part of the state. If in a real coffee machine, if there is no coffee, there should be a sensor that tells me that. There must be a sensor. Okay. I haven't included that sensor here. You could extend the model by including the sensor. It doesn't really make much difference to the model, but we have indeed looked at similar systems with sensors.
So you would have another component saying sensor is not on, and,
Yes.
and otherwise something else.
Another input,
Yeah.
sensor. Coffee, there is no coffee. And if there's no coffee, wait until the sensor has coffee, or the user does something different. Okay. If you don't include the sensor, some people don't for reasons of cost, or you just don't give the coffee out.
Yes.
Tough. I've experienced these machines myself. It's a commercial decision. But don't tell Microsoft. There's an interest, so you may have noticed these stars here. What the stars mean is that input is irrelevant. Do not consider that input. Okay, so this is an explicit, this is where the asynchronicity comes in. This is saying this rule will fire even if no button has been pressed. This rule is saying if you press the coffee button, even if the user isn't simultaneously putting in a coin, give them their coffee. This is what you expect. Likewise, on the output, where we have a star means nothing. Don't produce anything. 0 cost for that entity. So it's a way of saying, don't do anything, but still having a triple of results. Peter?
Are the matches tried sequentially?
Good question.
They overlap. And so
They do. The answer is yes. And the reason it's yes is because I've used the match keyword. In Hume, we also have the opportunity for fair matching. And with fair matching, then the order is a fair one. I don't want to go into the precise semantics of that. It turns out to be pretty complicated. And not everybody agrees exactly what fairness is. But we have a model of fairness. If you want fairness, you can have it. If you don't want fairness, you can have this design. So simply by changing this from match to fair, you get a fair design. But here we're going to take priority over the coins coming in before the button presses. From the model, it doesn't really matter too much, except that having the coins coming in before you try to dispense the coffee probably results in less frustration, if there's a choice. But that's a design choice. Sometimes you want one, sometimes the other. We have both. Okay, and then the vend function, basically what it says is check the cost, and if you have enough money in the system, dispense a drink, take the cost away, and don't return any money to the user until they press the cancel. You could, if you wanted, return the change. Some machines do this. It's just a matter of the logic that you've got here. Otherwise, if there isn't enough money, don't give a drink. Keep the value the same. Don't return any money to the user. And you could, if you wanted a slightly more complex system here, have a flashing red light that said, stupid user, you haven't got enough money, or words to that effect. This is just a small refinement to this basic model, to the basic design. Sharon.
I don't understand the interaction between stars and types. Given, for
Star
example,
star is of type alpha. It can be any type.
So like a type of a throw an exception.
Like the type of an exception. Well, it's a nothing.
if something thinks it's getting a drink and what it's gotten is a star, what does it actually have?
Nothing.
So everything's kind of implicitly lifted. It's not even a lifting semantics.
No, it's not even lifted.
There's this extra
It's
nothing
nothing.
value.
There is no value.
Okay.
Okay? There is no value. There is no value in the domain. There is nothing.
So that box would not fire if you were.
That box will not
The
fire.
box doesn't fire.
Or it doesn't produce an output. It's
Yeah.
Right.
nothing.
Okay.
Literally nothing.
Okay. So
Now,
the
in
way-
the implementation, there is actually something to represent nothing. That's not part of the
so I
type
should
world.
think of types as wires and box and star as being no signal was sent on this wire.
Yes.
Yeah.
Yes. Sort of. It's a little more subtle on the input.
If I
It's
have
ignore
one-
the input if it was sent.
Yes. Yeah. Right.
So if I make a mistake and put a star somewhere, I could sort of deadlock things.
It's possible to do that. It's actually, it is possible to deadlock Hume, but it's actually fairly hard because of the reactivity. Usually if you have a deadlock, it will lock almost instantly, and it's normally what you see is that you've consumed an input and not produced an output. So just by looking at the input and output traces, you see instantly, yes, there's a deadlock.
Yeah, no, I'm not saying it would be a subtle, tricky thing, just
So
that
it's-
a star going up would say, well, you know, this next guy is not going to fire, so I would observe
Yes.
being stuck.
Yes. It's stuck. It's not necessarily a deadlock, it might be what you intend.
Yeah, sure.
But yes, no output. Okay, I'm going to move on because I need to go on to the semantics. And I've got about half the time, I think. So we have a mechanism for exception handling. The point about this is that the exceptions have known cost. So the language is designed in such a way that exceptions have known cost. We also have a mechanism for dealing with time explicitly in the language. Here's another little example. This is taken from Bill and Lee. It's a digital watch, like the one I've got on my wrist. Basically a number of buttons, and I respond to the watches. And the key thing here is that I've got a tick, and here I'm streaming this from, I'm taking input from an external stream. If I don't get some input within 1 second, what I'm doing is basically to trigger a tick. So this is, every second there's a tick. This feeds in using the exception mechanism into the box, and the box then processes that, updates the time. So you have a heartbeat going here in your digital watch. Okay, so time is built in. And these constructs can be built into expressions as well as the triggers. The existence of a within construct initiates an analysis, and the analysis will check that the condition that's been specified is met. If not, there will be some exception. So you have the choice, yes, I can verify this. If I can't verify it, then the implementation will ensure that the condition that you specified is met by forcing some kind of well-known runtime exception, which can then be handled within known time, known space. This is how we deal with real-time exception handling within the system. Okay, what we're trying to do is to use the semantics approach. What I've got is an abstract machine, the Hume abstract machine. What I want to do is to expose the costs for abstract machine instructions correlated with real hardware costs. And the time costs we use an abstract interpretation tool. This is Absinth's AIT tool. This is a small step semantics. From the low-level semantics, what I do is to construct a language-level semantics, a big step semantics for the language that basically tells me what the execution of the machine is across multiple steps of the machine. And this is correlated with the abstract machine, and there's a formal translation from the language to the abstract machine level, which has been shown to produce the correct results with respect to the denotational semantics of the language. So we know that the translation is correct. It does the right thing, it has specific behavior, and we can prove what the behavior is. From this, we can then construct an analysis, an automatic analysis that tells us a priori what are the execution costs of a human program, again done fully formally and proven to be correct against the semantics. Okay, so here's what the abstract machine is all about. Essentially, it's a simple stack and heap design supporting all the things we need. The main purpose of the machine is not to be incredibly fast, but to be predictable, to have known behavior. You can always make it faster later, but if it's not predictable, it will never be useful for our purposes. So that's the point of the machine. This is showing you the internals of the machine. Essentially, you have an instruction space. Here's the box with some stack and heap plus some internal memory. All of these are bounded. It has some input and some wires. These are bounded. The wires connect to other boxes. These are the outputs. All of these are buffers. There is only one buffer for each input and each output. So these are fixed space. Okay, so fixed space, fixed time throughout the entire system.
What is the status of this abstract machine related to actual hardware? Because if you have an embedded system, it is really in relation to a specific platform that everything is going to work or not.
Yeah, I'll show you. I'll show you. There's some additional information. I don't want to dwell too much on this. They show you that there's some sort of register model internally with program counters, things to handle rules which deal with fairness, and some pointers to deal with matches, for example, plus a rather unusual pointer, the static link pointer, which is there to handle stack frames and to keep these bounded. Wire structure, very simple, essentially just a fixed size, telling you where the input comes from, where the output goes to, and some pointer into some memory where the actual data is held. It's a very simple structure, fixed size. Stack frames, we're using a static link pointer approach. So the idea here is to link the frames according to the static scope. And the main advantage of this is to avoid lambda lifting at the top level. And this makes the cost of closures much easier to predict in our system. It makes the cost of stack frames much easier to predict. We pay the cost of one pointer in each frame, but each of them then is fixed size. If we have lambda lifting, then we may have variable sized frames, which are harder to deal with. Let me show you about the machine instructions. This is coming on to what you're asking about. So here's a simple description of the machine instructions in a sort of pseudo-C. And I apologize for those people who do these things more formally, but this is the approach that people like Leonard Augustin have also taken for defining their semantics. And you can easily translate this into something more formal if you need to. We have done this. So for example, if I'm creating an integer, 32-bit integer, what I need to do is to set up a tag. So I'm setting up a tag, putting the value into the heap pointer, which is the tag. These are boxed values. You can have unboxed ones as well. The boxed ones are more interesting because they use heap. The stack pointer is set to point to that. There should be, yes, in 32i. So I'm having to allocate to the object in the heap here. The heap pointer is incremented by some constant, which is the amount of space that this takes on my implementation. Okay? And then I go on to the next instruction, and so on for all the other things. This is how we deal with time handling. So we set up handlers to deal with this. These are known units, known primitives. There are a lot more instructions. In total, there are about 70 instructions in the machine, so it's not completely trivial. But all of them have this kind of semantics. As you can see, very low level with costs that are easily derived, at least from memory. What we need to do is translate our program Hume source down into that. So here's a compilation scheme, formal compilation scheme. And for example, we can say, well, if you're compiling an integer what you do is you omit the makeInt instruction for that integer. Okay. And we can prove that that has the correct effect against the denotational semantics and using the operational semantics that I've defined. Functions are a little more complicated. I won't show you those. Here are the rules dealing with exceptions, just to show you that all these things are dealt with as part of the language. I'm quite proud of the exception handling. It was very tricky to get right. Just to tell you this isn't completely stupid, here's some statistics compared with an old version of Java and Ada. So the source code is 867 lines in Java. We have a Java implementation. 234 of those lines are real code. The rest is sort of type definitions, function definitions, class definitions, etc. In Hume, 251 lines, 51 of which are executable code. The rest are type definitions, box specifications, wire linkages, etc. In Ada, well, we couldn't get the complete program, but the core is about 206 lines. So clearly, we have something which is quite high level compared with typical approaches. The object code is about 2,000 bytes for Hume, 7,000 bytes for the JVM, which is supposed to be quite efficient and compact, and 12K bytes for the Ada compiled code. So quite compact. Memory requirements, the code, executing this code took 9 megabytes for the JVM. Using our prototype Hume implementations, it took 400 kilobytes on Mac OS X. It took 60 kilobytes on a bare real-time Linux system. Okay, so very compact. And it's about 12 times faster than the JVM. So there's something a bit weird going on with the JVM. That's not my problem. I leave it to the Microsoft people to improve it.
Question? Maybe I missed something. What was the benchmark? What was the problem?
The problem is it's one example, which is it's from Burns and Welling's book. I think it's Mine Pump Controller, and they only give the core code for the actual controller because the rest of it is just too complex in Java, I guess. So there's just the core code for us to compare with. That's why I can't do the complete comparison. I'd have to write another 600 lines or 700 lines of Ada, and I wasn't that excited by it. It wouldn't be a fair comparison anyway. But I mean, the key figures show the approximate. It's just an approximate measure for some simple example. So what we say with functional programming approaches is that the code is much shorter. Typically, we aim for something like a factor of 10 shorter. This isn't quite a factor of 10 smaller. And that's because we're having to deal with these low-level constructs. Because there's a lot of stuff in Hume to do with the box structure, to do with wiring. As the boxes, as you have more boxes, so of course you have more overhead. So there's a design decision about how many boxes do you have versus how big do the boxes get. Okay, so some interesting questions about compactness of representation versus structure of the code.
So these numbers are numbers for a simulator or are numbers for an actual implementation of
An actual
machine?
implementation.
What machine?
Well, in this case, on the Mac.
Oh, I see.
In this case, on an x86 box running real-time Linux. I took this implementation, I mean, it's not quite relevant to the talk, but I took this implementation and I ran it for 72 hours over one weekend. It was running on bare metal with my memory predictions, and there were no incorrect memory accesses. There were no memory faults. And every real-time deadline was met during those 72 hours. So it really is quite decent, but not that fast. Okay, predictable, not that fast. Go ahead.
Do you know what's the highest rate of inputs you can handle in your implementation?
We haven't really measured it, but we have done some real-time video. We've got some examples to deal with real-time video. Okay, so we can deal with real-time video with the right processor. Okay, so it's largely a matter of matching the processor to the application. But absolute performance isn't really what we've been aiming at just at this stage. just happens to be a statistic. Adrian.
I was a chip designer once. There are obvious parallels between what you have here and some hardware description languages. Have you got any plans to do direct hardware synthesis off the back of this? Because a lot of the hardware folk would be very pleased to have systems which were guaranteeing hard real-time constraints, and then all the performance problems go away because it's just running on an FPGA. Yeah.
Yes. Yes.
Is that actually the target, or is the target 8-bit microprocessor?
It's a possible target. So I don't really have time to go into it, but we have done some work on basically a cut-down version of the language that we call HW Hume, hardware Hume, which is a good language for describing these circuits. And you can indeed prove properties about the timing and about the circuits. There are also other similar languages, things like Lava, that Satnam Singh, Mary Sharon have been working on, for example, and Hydra that John O'Donnell has been working on. And these have a kind of similar feel.
And what do you do? Blow away the heap stuff and make it even more static than it already is? I mean, when you cut it down, what do you have to throw out of the semantics?
You can still have the heap. The question is what appears in the hardware. So you need to translate the memory operations into something which happens on the hardware. Okay, and this can be in terms of FPGA operations. If you've got VHDL, it could be a netlist. So I've got some examples of that. We haven't fully worked that out. So I can show you a paper from a few years back where I did basically what you're asking. But let me go on to the semantics. So Hume operational semantics. At the high level, basically what we've got is a semantics where we have a stack and a heap, V for stack, H for heap, where we're dealing with an expression of some form. So I'm talking here about the expression semantics, not the box semantics. What this does is to produce me a label in some new heap, and this is whatever has been allocated. So for example, in my integer example, what I'm doing is to allocate a new object, put it in the heap, and to update the stack location. So that's what happens here. So the thing, this represents the top of the stack. L is the top of the stack after the execution of this instruction, of these instructions. N and N prime are the associated costs before and after the step. So what this does is to help me build up a cost semantics at the language level. So what I'm doing is to say, I need this amount of stack, heap, whatever, before executing this expression. Afterwards, what I have is N prime amount of stack, heap, whatever. Simple example, here's my rule for an integer, making an integer. What I have is I have a stack, initial heap. I'm constructing an integer n. This is going to give me back a label where the label points to the integer n constructed in the heap. And then what I have to be sure of is that before executing that instruction, I have whatever the cost of making an int is. So k muk int. I'm going to leave that abstract here. But for example, if I'm talking about stack, this could be 1. I'm pushing one thing onto the stack. For heap, it's going to be whatever the cost of the heap creation is. And we have rules for all of these. This is an interesting rule because what it's saying is you have to thread the cost from Q1, so the initial cost is Q1. We get back, having executed E1, some cost Q2. This is fed through the execution of E2, and we get back Q prime. The micro costs, k let 1, k let 2, these are costs that some machines might introduce at each of these points. Some of the compilation schemes might introduce in terms of actual machine instructions. So all of these have to be costed. If you're just dealing with stack, maybe a lot of these costs are 0, but we're trying to make this generic. How do we get the costs? Well, we measure them. So here is a complete table. You probably can't read all of this from the back. But for example, what we're saying is the resource usage of the muk int in some context, so we're having to include some contextual information to disambiguate the instruction, is whatever h int is, which is the costs that I had earlier on in my semantics, my abstract machine semantics. Okay, you can prove the correspondence of this with machine semantics. Likewise, this is a bit big, we can do the same for stack, and we can see that the cost of the stack for the look-int is 1. So these are relatively trivial costs. Some of the costs down here are a little more complicated. You can see there's some side conditions. Basically say, well, depending on the context, depending on what instruction exactly you're executing, what the parameters are, these are more complicated. These have bigger or lesser cost. But there is a complete cost model for all the instructions. That's fine. The time costs we obtained from the actual instruction implementation. And as I said, we use Absinthe AIT tool to derive these from the machine code implementation for each instruction. So it is not for a program, but on an instruction by instruction basis, so that we can reuse the effort in doing the costing. We do the costing once, and then you can reuse it for any program. And any abstract machine implementation will let you do this. We have to do this for each ham instruction on every architecture that we're interested in. Mostly it's tedious, sometimes it's very hard. I was having a discussion with someone where I explained, well, we had an architecture and we wanted to know what the cost was of a floating point sign operation. And to do this, we had to prove that one of the internal loops in the library, which was unbounded, actually had a finite cost and what the limits were on that cost. So I actually had to dive into the instructions in the library, integer instructions in the library, and basically demonstrate what the cost was of those instructions. That was pretty hard and very tedious. It took about a week or two just for one instruction. Okay, so this is not easy. It takes a lot of effort, a lot of time, but you only have to do it once for each architecture. And we've verified these times experimentally on some actual machine architectures, Renesas M32C, a PowerPC 603, and an FPGA architecture that we've targeted. Here's an example of the instruction timings for one of these architectures, Renesas M32C. So this is a real-time microcontroller. It's a KISC machine widely used in microcontroller architectures. So what you can see is we've got a complete table, more or less complete table for all of the ham instructions. And the cost of our look-int turns out to be 84 clock cycles. So this will scale according to the processor speed of the particular machine that you're dealing with. And then from this, what we do is construct an automated analysis using an amortization technique. The idea of the amortization is basically to balance out the costs so that I can prepay some cost that I'm later going to use. So I won't go into the details. Hopefully people roughly know what amortization is anyway. If not, there are plenty of papers about it. What we do is we turn this into a type system. So here's what my analysis rules look like. I have a source expression, which I'm analyzing. I have the type context gamma. I have some type A that I'm deriving. And what I'm going to do is to work out the potential cost before and after execution from my operational semantics. So basically the analysis follows the rules of the operational semantics and at the same time producing annotated types within which there are constraints on the types that tell me about the execution costs from my semantics. Okay? And as we've seen, this all ties down from the physical hardware all the way up to this analysis. Sure.
Do you bake in a particular style of amortized analysis? Is this like Banker's method is built in, or how flexible are you about the kinds of amortization you can do?
It's a particular style of analysis. I'm not sure it's particularly based on the Banker's model. You need to talk to Stefan about that. But you have to. Only some types of amortized analysis are analyzable. Okay, so you have to do exactly what we've done.
So
I'll give you the paper.
Algorithm basically
There's an algorithm
hiding behind the type system, and to satisfy it, you have to basically.
This is the type system. Underlying it, there's an inference algorithm. The inference algorithm is derived formally. We have shown the soundness of that algorithm against the type system. So again, this is all fully formal. So here are the rules. This is basically saying that all of the possible valuations satisfy the constraints that I'm deriving. Don't worry about the detail here. This is just to show you what the types look like. The key things are that we're annotating function types with potentials. This allows us to deal with higher order functions. It allows us to pass costs through different function calls. And we're also annotating costs for constructors so we can get potential costs relative to the number of constructors in the program. Example of a rule here, this is a very simple one. For the mockint, for the int case, what I'm doing is to derive the cost of k mockint, and there's nothing left afterwards. I don't need to return anything after that. So it's a slightly simpler version of the operational semantics rule. The rule for the let binding, again, basically threads the cost through. So in this case, it derives pretty well closely from the operational semantics. It's easy to show the correspondence between the semantics and this. Function rules are more complicated. I won't go into the details here. This took quite a lot of time to sort out. And one of the interesting points is to do with substructural rules, which allow us to weaken the cost in arbitrary situations. So relax allows us to increase costs when we need to do this for analysis purposes, and sharing allows us to capture sharing information so we can split the cost between different uses of a function, for example, or different uses of a particular data structure. So these are two critical rules that we have to use very carefully to get good cost information out. Simple example, reverse append. What we do is to run this through our analysis. What it does is to give us back a type. What the type says here is that the cost is 2/0. What this means is that every, and the for each cons in the input, we have to pay 4. So what this is basically telling us is that the heap consumption is linear in the input size. It's four times the length of the input plus 2. Okay? And that is, in Hume, words of memory. Here's a similar example of the control box. I'll just skip over this for time reasons, but just show you that the control box is perfectly analyzable. This one's interesting because it has some alternatives here. So it says 1 if the second wire is live, 0 if the wire is void, and x2 is 1 if the third wire is live, otherwise void. So there's some conditional costing going on in this case. Just want to quickly show you the results. So this is for one example, sum of squares, simple arithmetic calculation. Here are so we've got the number of calls. This is showing the heap usage. This is the predicted analysis result. This is what we actually measured in some execution of the Hume machine. What you can see is this is pretty accurate. This is something with unfold, map, and fold. So this is a higher order definition. This has higher order definition. The stack cost, again, is very accurate, within 4%. The time is slightly less accurate, but still within 30% of the actual measured cost. Okay? It's worth pointing out that the measured cost is not necessarily the worst case. It's just the worst that we observed when running the program a few times. So that is not a guaranteed worst case. It's just a measured worst case over a few executions. It doesn't mean the analysis is wrong. It simply means that it's allowing for some things that might not have actually happened in practice. This is, again, showing some results for higher order functions. I'll just skip over that. If you want to read more about what we've done, there's a Popple paper from a couple of years ago. This is talking about higher determination of resource usage for higher order functions. It deals with the stack, the heap, and the time, together with a companion paper from FM from the same year. It's also possible to extend this to lazy evaluation. It's quite fun, but I really didn't have the time to show you that in this talk. Essentially, what it involves is fiddling around with the idea of potential. So we prepay some of the costs of allocating a thunk, and then we share this according to the semantic rules. There's a paper from ICFP last year about this. What we're planning to do is to build up a more in-depth version of that that has, for example, some of the stack and the time information in there as well. Oh, just to show you that Hume is quite good, it really does do real-time stuff. I've sort of given you an example. Here's one of our little experiment that our colleagues in France did. This is an inverted pendulum, which is being controlled by this computer here, this box, in fact. So this is without Hume. It sort of flops about, uncontrolled. And the version over here is with Hume, and what you notice is that Hume correctly maintains the stability of the pendulum in the vertical direction, basically by moving the motor around. It's only controlling 2 degrees of freedom. The third degree of freedom, as you can see, is unconstrained by this particular model. So at the end it just sort of wanders around a bit. We weren't trying to control that, but we did keep the pendulum vertical in real time.
What happens if you hit it?
Well, it's probably going to have to. I'm not sure the model accounts for that, Adrian. You probably need a more complicated model. If you can recover from it, then it will probably recover from it. It will see the deviation and it will attempt to recover. But I'm guessing there's then going to be some sort of feedback loop whilst it stabilizes. Maybe it can never get it back. Depends on the model that you're using. This is a PID controller model. So conclusions. What I've done is to show you a semantics-based language definition for Hume for bounded time and space. We have semantics at all levels, so we have a static semantics, we have a denotational semantics, we have an operational semantics, abstract machine semantics, a formal compilation scheme. All of this is proved correct at all levels, and there's some sort of Isabelle model of this that you can use to reason about resource consumption as well. So a lot of semantic stuff there. Very good formal cost models dealing with dynamic memory allocation, exceptions, recursion, higher order functions, lazy evaluation. And these are extensible. So we've dealt with stack, time, and heap allocations, but they can be extended to deal with power, for example, and they are in principle applicable to other languages too. So it's not just Hume that this applies to. Of course, you probably need a similarly strong semantic model for all these other languages to make them work effectively. That's another story. Here are things that we're interested in doing. Firstly, a couple of related pieces of work. Nonlinear balance has been looked at by Hoffman, Ehrig, and Hoffman last year, Popper 2012. It would be straightforward to incorporate those into the cost model. Nothing intrinsic about this restricts it to linearity in terms of the cost bounds. Brian Campbell, who's in the audience, has an interesting mechanism for that can improve the cost for stack. We haven't incorporated that yet. It'd be quite interesting to do that, possibly in this mega paper that we plan to write in the near future. I've shown you allocation, but not reclamation. In fact, I mentioned at the start that Hume actually has quite a clever scheme, because when we execute a box, what happens is we consume input, we process it, we produce output on wires. The input wires and the output wires are fixed size. Having produced the output, we can throw away all of the heap and stack usage within a box. So essentially what happens is the heap within the box is copied. The values that are live are copied from the heap within the box to the wires. If we have state, we feed them back. So we get an automatic, as I said, copying, compacting, garbage collection within box iterations, which we can also cost in real time. So quite a neat mechanism. You might still want garbage collection because within the box, you might be writing recursive code. Okay, so then you might want some garbage collection within the box. Martin Hoffman has looked at this recently using a region-based mechanism. I've done some work on region-based allocation. It looks entirely plausible to put that in if you want. We're also interested in multi-core, many-core. So what I'm showing you is highly concurrent, easily applicable to, easily scalable, can easily be applied to multi-core, many-core architectures. And the lazy evaluation work, of course, obviously we want to target Haskell eventually to show that Haskell is costable. Some more papers if you're interested in reading them. Here's why I think this is relevant to scalable language specification. Well, Hume is scalable, so it's a scalable language that has been specified. Sorry, Peter. But also, a lot of the things that we've done are to do with semantics, they're to do with compositionality, scaling. These issues are all critical to scaling. So I think that's why what I've done is relevant to this workshop. So thank you to our sponsors, and thank you to the audience.